continuation of Preview Chapter P, Section 5 on solving systems of equations. We've already looked at one method, the substitution method, for solving systems, and we now want to look at a second method called the elimination method. In this method, our goal is going to be to use multiplying one or both equations by some number that's going to cause a variable to be eliminated when the equations are added together. So this is our goal. We want to cause one variable to be eliminated when the equations are added together. We know that we're allowed to multiply an equation by any number we want, as long as we always multiply by the same thing on both sides. So we've got to keep that in mind as we try to create this elimination process. Looking at our first example, we have to start by choosing a variable that we would like to eliminate. I'm going to work with the x's. A couple things appeal to me. First of all, I've already got one negative and one positive, which means it's going to be a little bit easier, perhaps, to get them to add up to 0 or cancel each other out. And they're also smaller numbers, which I also like. So the first question I'm asking myself is, looking at that 2 and that 3, what is the smallest number I can think of that's both of these numbers go into evenly? That's a multiple of both of these numbers. And the answer would be 6. Both those numbers go evenly into 6. So I'm going to try and create a positive 6x and a negative 6x. On my top equation, if I were to multiply by 3, I would get that negative 6x. So let's do that. Negative 6x. Continuing to multiply by 3, plus 9y equals 27. In my second equation, here I'm going to try and get a positive 6 to eliminate the negative 6. And I can see that I'll need a multiplier of 2 to do that. So there's that positive 6x. Continuing to multiply, I would have the plus 14y equals negative 4. All right, I'll now add my equations together. Negative 6x and positive 6x add up to 0, just like we planned. And then we'd have a 23y equals 23. And dividing by the 23, that's going to give me y equal to 1. So I know the value of one of my variables now, and I'll just substitute to get the other. You can use either equation, doesn't matter. Either of these. I'll just use the bottom one here. I have 3x plus 7 times y, which I now know to be 1, equals negative 2. And let's see, solving that, I'm going to have 3x equals negative 9, and so x would be negative 3. So these two lines, if I were to graph them, would intersect at this point, negative 3, 1. That point is a solution to both lines, and therefore it's a solution to the system. We could check this on a calculator, but it would be a lot more work than the last one that we did, because we'd actually have to solve both equations for y first. So I'm actually not going to check this one. I'm going to assume that we've probably done all of our math right and we're okay with it. All right, toward the bottom of the page here is an example of an application that results in a system of equations. Let's take a look at that. We have a product that can be packaged two ways: small quantities in cardboard boxes, large quantities in wooden crates. A shipment containing 17 boxes and 8 crates weighs 285 pounds. A shipment of 9 boxes and 15 crates weighs 420 pounds. We want to find the weight of a box and the weight of a crate. So those are my two unknowns. And I tend to like to use variables that help me remember what's what. So I'm going to go with B for the weight of the box. And then I'll call C the weight of the crate. Those are the two things I would like to find out. All right. I've got two different sort of situations that were shown to me. Let's start out with this sentence right here. We know that the total weight for 17 boxes and 8 crates is 285 pounds. So 17 times B is going to give me the total weight of all the boxes. Plus, I have to add in how much the crates are going to weigh. 8 of them weigh C pounds each, so 8 times C. And together, I'm told that those total 285 pounds. Now, the next sentence tells us 9 boxes and 15 crates is going to weigh 420 pounds. So go ahead and write a sentence, or a number sentence, actually, an equation for that. 9 boxes would weigh 9 times B, plus our 15 crates, 15 times C pounds each, for a total of 420 pounds. All right, same idea as the last problem. If I would like to solve and find both B and C, a B and a C that work in both equations, I'm going to try to eliminate one of the variables. Again, it doesn't really matter which one. I'm going to go with the C this time, just slightly smaller numbers, but it really doesn't make any difference. You can work with whichever one you prefer. If I want to eliminate the C, first thing I need is a common multiple for 8 and 15, and it's nothing I really know off the top of my head, so I'm just going to go ahead and say, well, gosh, I know that 8 times 15 is 120. So why don't I just use 120 as my common multiple and try to get negative 120C on one of the equations and positive 120C on the other. On the first equation, if I were to multiply that 8 by 15, I know it's going to give me the 120C that I need. So let's do that. Multiply the whole equation by 15. Little arithmetic we're going to have to do here, so keep my calculator handy. 17 times 15 gives me 255B. Plus I already know 8 times 15 is 120C. And then 285 times 15 is 44,275. All right. In the second equation, essentially I want to do the same type of thing. I want to make 120 here, so I might think of multiplying by 8. But if I do that, 15 times 8 is going to give me 120C again. The problem is that the variables won't eliminate or add up to 0 unless one is positive and the other one is negative. So let's fix that by multiplying by negative 8 this time instead. 9 times negative 8, so negative 72B. 15 times negative 8, negative 120C. And then 420 times negative 8. My goodness. Negative 3,360. All right, looking pretty good. I'm going to add up these equations. So I got to take 255B minus 72B is going to be 183B. Positive and negative 120 adds up to 0. And then I've got my 4275 minus my 3360 is 915. And if I just divide both sides by the 183, That gives me b equals 5. So the weight of a box is 5 pounds. We'll write out the answer formally after we're all done, but let's get the c value before we do that. So again, it doesn't matter which equation you substitute into. I'm going to use the second one. We now know that b is 5, so I'll put that in. See, 9 times 5 is 45. And I'm going to have to subtract the 45. And so 15c is going to equal 375. And if I divide by the 15, I get 25. So our result is telling us that b, the weight of the box, is 5 pounds. And c, the weight of the crate, is 25 pounds. So that's our elimination method, trying to get one variable to add up to 0 or eliminate when the two equations are combined. There are a couple of special cases that we haven't yet talked about. We already know that systems of equations can be solved by graphing. We looked at that last time. And that this is usually only an efficient method if you have a graphing calculator or a computer program to help you. Graphing accurately enough by hand is generally not possible, or at least not efficient, in terms of a way to solve these systems. If you do need to do that, though, if you do have a graphing calculator and you want to do that, we went over the steps in the previous, in Part A of this section's video. All right, the question that we want to address here to finish up this section: will every system of linear equations have exactly one solution? Let's try to answer that question by considering these two systems. The first one has the two equations, negative 4x plus 2y equals 6, and 2x minus y equals 1. Those are the graphs associated with those two lines, and you can see that the lines are parallel. Since we've seen that the solution to the system is the intersection point, or the point that the two lines have in common, we can see that this system is not going to have any solutions. The two lines never cross. There's no point that belongs on both lines. So the system has no solution. Sometimes we call the system of equations inconsistent. All right, what about the second situation? In this case, what happened is I've got two equations here. Y equals 3 halves x plus 3, and 3x minus 2y equals negative 6. And yet, when you look at the graph, it looks like I only graphed one of them. What actually happened here is when we draw those graphs, they're going to graph right on top of one another, because in fact, they're actually the same line. If we take just a moment and do the algebra to solve the second equation for y, I would start by subtracting 3x, and then we divide by negative 2. So I end up with negative divided by negative is positive 3 halves x. And again, negative divided by negative is plus 3, which is exactly the other equation. When that happens, you have two equations, but they're truly the same, so the lines, when they graph, are exactly the same. We say we have infinitely many solutions. All of the points on the line satisfy both equations. this case, the original system of equations is called dependent. So to finish up this section, let's look at two examples of systems of equations. And algebraically, I want to see how we'll know when one of these two situations pops up. So let's take a look at the first one. This one we said when graphed actually turns out to be parallel lines. So the system had no solution. What happens when I take that exact same system and try to find a solution? I'm going to go ahead and use the elimination method on this one, and I'm going to focus on the y values. I can see that if I just multiplied the second equation by 2, I would have a positive 2y here and a negative 2y there. And that would eliminate the y values. So let's do that. I'm going to leave the first equation exactly the way it is. And the second equation I'm going to multiply by 2. That's going to give me 4x minus 2y equals 2. What happens when I try to add or combine these equations is that not only do the y's add up to 0 like we planned, but the x's add up to 0 as well. So the whole left side of the equation adds up to 0. The right side adds up to 8. And of course, that's a pretty strange looking equation since we all know that 0 is not equal to 8. When you get a false statement like this, all the variables have eliminated, and you just get one number equals another and it's not true, that's going to be how you'll recognize a system of equations that has no solution. All right, how about this other one? These two equations, we actually looked and saw they really were the same. And therefore, all the points on the line, infinitely many points, are solutions to that system. But how would you recognize that if you started to algebraically solve the system and not graph it? This particular system is set up really well for the substitution method. It's already solved for y. So I could take what y equals and just plug it in for the y in the second equation. That second equation is going to become 3x minus 2 times 3 halves x plus 3 in place of the y. And that's supposed to equal negative 6. I'm going to distribute the negative 2. So I have 3x. Negative 2 times 3 halves. The 2's would actually cancel. So I'd have negative 3x. And negative 2 times 3 is negative 6. On the left-hand side, 3x minus 3x is 0. So all I have left is negative 6, which is also what we have on the right-hand side. Now that certainly is a true statement. However, there are no variables left. I haven't been able to solve for x. When that happens, all the variables have eliminated, and you simply have a true arithmetic statement left. That's how you're going to recognize the infinitely many solutions or dependent system case. All right, this finishes up Section 5, and so we'll go ahead and get into the preview chapter, Section 6, in the next video.